Today we are starting with the unit 2 of mathematical modeling. Mainly we will discuss here and about the random number generation, about two procedures related to random number generations. Okay, so the standard reference book which we will be following here is this one, a first course in mathematical modeling by this authors. Okay, so basically today we consider the generation of random numbers, right? So randomness means actually indeterministic. Indeterministic means, that means suppose we are performing an experiment, and before we perform the experiment, so suppose you are measuring the length of a rod. Okay, so we know once we measure the length of the rod, we know ki suppose it is 5 centimeters, suppose. So even if you measure the rod second time, third time, any number of times, and if no force is acting on the rod, then definitely how many times you measure, it doesn't matter, every time you will get the length to be 5 centimeter. Okay, so the experiment of performing the measurement of the length gives you the output which is deterministic, that is 5 centimeter here. But suppose you are now tossing a coin, we know it is a probabilistic experiment because the outcome we cannot say beforehand whether it will be head or it will be tail. So actually if I consider this occurrence of head or occurrence of tail, say suppose I am repeating the experiment n number of times, where n can be very large quantity, then the outcome of head occurring or the outcome of tail occurring sequence, from this occurring we get a sequence of random numbers. So suppose I say head as, if head occurs I say 0, and if tail occurs I say 1, then we are getting a random binary sequence. Why random? Because from beforehand you cannot say whether you will get head or you get tail if the coin is unbiased. Okay, that means if you are tossing a fair coin. Okay, so here we get the idea ki, okay, then whenever we are dealing with a probabilistic experiment, definitely we are going to get something unpredictable, that means indeterministic. Okay, so here comes the idea of randomness. So basically what we are going to do today, we are just going to discuss some methods related to, or rather which will be used to generate real random numbers. Okay, so basically as I am saying ki we will be dealing with a sequence of real numbers. Sequence means the random number generator. For example, just I gave the example of the coin toss. What you are getting, a random number 0 1 0 1 0 0 1 1, like this. We do not know what you will be getting after this. Okay, so we are actually generating a sequence of real numbers. Okay, so we will see here ki how we can generate this sequence of real numbers randomly. Okay, and the utility of this is that this random number generators will be used in various simulation algorithms, and such as the Monte Carlo simulation. This is why I have given a specific example. There may be many examples. Okay, so now for the time being, let me just first let us try to understand ki how we can distinguish between random sequence and not a random sequence. Okay, so first I have given an example ki suppose you are taking xn, where xn you are taking to be n. Okay, xn you are taking to be n or 1 by n. That means what? If I take xn to be n, then you know ki what will be my sequence, 1 2 3 like this. And if I take 1 by n, then 1 half, 1 by 3, 1 by n. So actually what you have a recurrent formula which will tell you ki what will be your x0, what will be your x1, what will be your x2. So once you have the recurrent formula, then definitely what the numbers you are writing in the sequence, you have every knowledge about those numbers. Okay, that means you know the pattern of the numbers coming. And another thing you may see ki if I am just saying ki minus 1 to the power n, okay, then definitely what you are going to get, you are going to get a sequence of plus minus 1. Okay, so the main thing is that ki numbers may repeat, but there is a certain pattern. It may not repeat, even then there is a certain pattern. So in these cases where the pattern is known to us, we are getting a not a random sequence. If you can see from here, we are getting a not a random sequence. Okay, now because the pattern is known, now you consider this example. Suppose I have written the numbers 1 3 5 7 8 12 like this, and then dot dot, that means it goes on. Okay, can you say what is the pattern of writing these numbers? like this, where you know, once you know this pattern, you can write all the numbers starting from x1, x2 and x3 like that. Can you say any pattern for this one? Okay, you cannot find out any pattern for these numbers which I have written like this. So this sequence of writing these real numbers is unpredictable. It doesn't follow any pattern. There is no recurrence formula. Okay, so this gives the idea ki what I want to mean by the random sequence. Okay, but in originality, the main fact is that we cannot generate truly random sequence. That means genuinely random sequence we cannot generate with real numbers, with complex numbers, with anything. Actually, in the classical world, we cannot generate anything which is genuinely random. Okay, actually then we are dealing with the concept of pseudo random sequence. Pseudo random means what? It looks like random, but it is actually not random. Then you may ask why it looks like random, because we do not have the whole information about what we are writing down. If we have the whole information, then definitely we can find out the pattern or search the pattern in it. For example, I just give the example of this one, 1 3 5 7 8 up to 12, right? Then you see I have given 1 3 5 7 8 to 8 na sorry 18 whatever 18 12, and then dot dot I am writing. So whenever I am writing this sequence for the first time up to this number of elements and then putting dot dot, then up to this knowledge this sequence is random. But if I increase my knowledge, so suppose I write some, I have written 6 numbers here, let me write another 6 numbers, this, and suppose the sequence is like this key. First you are writing 1 3 5 7 18 12, then again 1 3 5 7 18 12, then again 6 numbers 1 3 5 7 18 12. So now and then putting dot dot. So I am writing, instead of 6 numbers of the sequence, I am writing 18 numbers. So now you can see there is a pattern which we missed here. Why we missed here? Because there was incomplete information. We provided extra information here. From here to here we provided extra information, and now we are getting the idea, oh, there is a pattern here, and the pattern is this much, and this much. They are all repeating. That means in short you can write like this ki xn equals to 1, xn plus 1 equal to 3, xn plus 2 equal to 5, xn plus 3 equals to 7, xn plus 4 equals to 18, xn plus 5 equal to 12, where your xn is varying between this n equals to 1, 7, 13 like that. Okay, that means what? Whenever I am giving you extra information, the sequence which seemed to be random, which appeared to be random, is now becoming deterministic. So this type of sequence is said to be pseudo random sequence. Actually in reality, whatever real numbers simulation we do in any practical problem related to the classical world, obviously we are dealing with pseudo random sequence. But actually what happens, the length of the sequence is so much large that even if you encounter a sufficient length of the sequence also, you do not get the pattern. So that is the trick which plays the role of this randomness here. But in general we are dealing with pseudo random nature. Okay, Acha. Now so this convention in the pseudo random is considered to be random. Okay, actually they are not actually random, but we suppose up to our purpose we say to be random. The main motive is to keep the pattern unknown to the user as long as possible. Okay, so you make it so much complex. So suppose instead of 6 numbers I give some more numbers where there is no pattern in it. So suppose I get 10,000 numbers where there is no pattern, and after 10,000, from 10,000 plus one number, again those 10,000 numbers are repeated. Okay, so you have to wait up to that 10,000 plus 1 so as to get, okay, the pattern is again coming back. Okay, so now you think if I want to generate something which is at least seems to random, then we have to increase the length of unpredictability. Okay, so here we first learn the method of, actually up to your syllabus we will learn 2 methods for the random number generation. One is the linear congruence method and another one is the middle squaring method, I say. Let me just see what is there. So the most important of these two is the linear congruence method. So as we are saying, we will try to generate a sequence of real numbers which will at least seem to be random. Okay, so let us go into it. Then this one. Okay, so the linear congruence method was first introduced by this scientist, whatever, and the majority of pseudo-random numbers used today are based on this method. As I already said, it is used in various simulation algorithms, mainly the Monte Carlo simulation we will see. Okay, so one advantage it has over other methods that seeds can be selected that generate patterns that eventually cycle. Okay, however, the length of the cycle is so large that the pattern does not repeat itself on large computers for most applications. That is what I wanted to mean before. You have to try to make the sequence so large such that even if there exists some pattern, by running the program within a sufficiently small steps, you cannot understand it. For example, I do not mention the method. Suppose I generate a sequence such that 10 to the power 5 terms are not maintaining any pattern, and suppose my computer in which I am running it can just control up to 10 to the power 4, just can scan numbers up to this amount of this length of the sequence. Okay, so and I have generated a sequence somehow which will not give any pattern until you have gone up to 10 to the power 5 plus 1 numbers. Okay, so in that case, if my computer is unable to read so much numbers, it can read up to 10 to the power 4 numbers. So suppose up to this length my sequence is random, but the computer or any system which you are using can read up to this amount or this length of the sequence. So anyone who is using the computer, what he or she will get the idea, okay, the sequence we are dealing with is random, but actually the sequence is not at all random. If I can use some more better system which can read, say suppose 10 to the power 8 terms or 10 to the power 10 terms, then obviously we get the idea ki okay, the sequence which is generated by the algorithm which we are using is not at all random. It is repetitive in nature, and after some time it will repeat back. So this cycle means a cycle of repetition. You are starting from here and you are coming back here. So this coming back here, we will try to increase the cycle's length. Okay, the better algorithm is one which can give a cycle of larger length. So the linear congruence, we will see कि we can increase the cycle's length because there will be some parameters controlling which we can increase the length of the cycle, unlike any other method. So this linear congruence method is mostly used. Okay, so what is the method? Let us just go into the algorithm of it. The method requires the choice of 3 integers a, b and c. As I said, there will be some controlling parameters, so a, b and c. Given some initial seed, seed is nothing but suppose you are I am talking about sequence, you consider seed as the first element of the sequence, x0. So these 3 integers we will choose, choose, and that another thing we have to choose the initial seed from which our sequence will begin. Okay, so the algorithm says कि in the linear congruence we will use or generate a sequence via this rule. What does the rule says? कि xn plus 1 equal to product of axn plus b modulo c. Okay, so you see this a, b, c parameters are there. You start with x0. So suppose a, b, suppose you consider this example only, a equal to 1, b equal to 7, c equal to 10, and I start with the initial seed. So suppose what they have taken, suppose you take any one, I just want to go through this. So suppose x0 equal to 7 you take. Okay, so x0 equals to 7, 7 into 7 equal to 1. So 7 into, here I say x0 I have taken to be 7. Okay, and a equals to 1. So a into x0 is 7 only, plus b is 7 again. So 7 plus 7, 14. And modulo 10, that means what it will give? It will give the remainder when you divide by 10. So 14 divided by 10, it will give you remainder of 4. So x1 will be your 4. Okay, again using x1 as 4, putting here 4 into 1 plus 7 modulo 10, it will again give you the next number. So this continues. Okay, so actually I have shown it below in details, whatever their calculation they're saying here, just I have shown it in explicitly. So I have taken A1, B7, C10, just exactly what they have said there, and the initial seed also they are using, I am using it here, x0 equal to 7, so x1 comes to be C, 1 into 7 plus 7, so 14 mod 10, that means 4. Then again using 4 from here to here, because x1 will be used to find out x2. So again 4 into 1 plus 7 mod 10, that means 11, so 1. So again 1 will be used, 1 into 1 plus 7 mod 10, so 8, and this continues. Achha, how long this continues? First and foremost of all, this can continue infinitely, no harm in it. But the thing is that as I said before, the pattern will be recognized after some time. So whether using this linear congruence method can we recognize the pattern after some terms? Answer is yes, we can recognize. It depends on the length of the cycle. That means actually it depends on this modulo C which you are taking. We are quite aware of the fact that whenever we divide any number by C, then the remainders can be what? 0, 1, 2, 3 up to C minus 1. So here comes the idea of the cycle. After that, again we will be repeating 0, 1, 2 up to C minus 1. Okay. So here the repetition comes into existence. The cycle comes into existence. Okay. So here also the same thing is happening. See, x0 up to, here C is 10. So according to that rule, how much should be non-repetitive? Up to x9 it should be non-repetitive. See, x0 is 7, x1 is 4, x2 1, x3 8, x4 5, x5 2, x6 9, x7 6, x8 3, x9 0. Now you see x10 7, but 7 already we have got here. x11 4 already we have got here. One thing let me just remind you, I am not saying ki once you get any number which is repeated, then only you are going to say ki okay, then I am getting a cycle. Not that. In this method particularly, we are seeing ki the way of construction says ki once you are getting repetition, in this method I am saying again, in the linear congruence method, once we are getting repetitions, according to the formula we are using this formula. So that gives idea ki as we are generating the remainders when divided by C, so when we are getting something which is repeated, that gives the idea ki okay, the cycle is once crossed and we are again repeating the cycle. Okay, so here x10 is 7, but 7 is already obtained as a remainder before. In fact it was x0 itself. So the repetition has started. So x11 is giving you 4 also is already obtained in or as x1. Okay, so the repetition has started after you cross x9. x9 means 10 terms. Okay, so obviously for 10 terms you should be getting again back the same remainder because you are dividing by 10. So again x10, x11, x12, and this continues. So the pattern, how is the pattern? You can write like this: 7 4 1 8 5 2 9 6 3 0. Then up to 0 there is no repetition, nothing. Again after 0, 7 4 18, like this. So now suppose you think if for C equal to 10 this is occurring, if I make C equal to 10,000, then you can easily understand how long this non-repetition will go, and then it will repeat. So if my system is not capable of reading so many numbers, then up to that system this sequence is random. But if I use a better or a more efficient system, then in that system can decode ki this sequence is not at all random, it is repeating after 10,000 steps. That means it is a pseudo random sequence. Okay, so here lies the idea how we use the linear congruence method to generate pseudo-random sequence of real numbers. Okay, and what is the important thing here? As I already said, or they are all saying here, two things are important. One is the cycling nature. This one, cycling means the sequence repeats itself, and although undesirable, it is unavoidable. Undesirable means obviously we are trying to generate what? We are trying to generate unpredictability. That is, we are trying to generate random numbers, that means numbers which you cannot predict, the user cannot predict. But due to this cycle, that is the repetition, after some stage, definitely we are getting the idea, oh, okay, this cycle is repeating after this. That means up to, so suppose 10 numbers, it will be like this, again 10 numbers will be like this, and again 10 numbers will be like this. So we get the idea. We do not want that, but as I already said, you cannot avoid that thing. Okay, at some point all pseudo-random generators begin to cycle. Okay, and for the linear congruence method, it begins to cycle depending on the C's length. That means modulo C, whatever C's value you are putting, it is very crucial or important for the linear congruence method. Okay, so the thing here we have already said it. Okay, Achha, now we will see how we use it later. Let us do one problem related to it. So suppose use the linear congruence method to generate 10 random numbers using a equals to 5, b equals to 1 and c equals to 8. So the parameters are provided. Initial seed is your choice. You choose it. Okay. What we have asked to do? We are asked to generate 10 random numbers. Achha. First and foremost of all, you see c is 8. So actually non-repetition should exist up to 8 numbers. That means up to x7. After that it will repeat. So 3 out of 10 random numbers, 7 will be non-repeative, and again the remaining 3 will be repeating. Okay. So let us see how we are getting it. So a equal to 5, b equal to 1, c equal to 8. Initial seed, I am taking this x0. Okay, actually I am just writing it in the form of how you write an array, because in an array we know it, we can store many block of numbers. So I am taking that data structure here to just write the algorithm. Okay, so x0 I am taking 6. It may vary, it doesn't matter. So x side, that means I am using the recurrent formula here, is modulus of a into x I minus 1 plus b with respect to c. So this is actually a x I minus 1 plus b mod c. This is written like this. Okay, I am writing like this. So the output, what you will get if you run this algorithm, you will get this output C6745230 So up to this there is no repetition. You have taken C to be 8. So how many numbers should not be repeating? 8. Okay, so this 8 numbers, and then again it starts repeating. Okay, so up to 10. After 8th term, repetition starts. So cycling occurring after x7, that is 8th term. So 9th and 10th, x8 and x9 is again any of these two numbers. So 6, 7. Okay. Again, suppose for this one, a equal to 1, b equal to 7, c equals to 10. So now you will see the output here. Again the same method I am using. I am taking the same initial seed so as to show that the initial seed is not the matter. The main matter is this c. Okay. So here c was 8 and here c is 10. Now you can see the length of the sequence in which the pattern is not coming, it will be increasing. Here there were 8 numbers for which there was non-repetition, and after that cycling has started. Here there will be 10 numbers. Okay, here there will be 10 numbers. What are the numbers? See, 63074185229. Okay, up to this. Then again it has started repeating. See, 63074 like that. Okay, so cycling over here after x9. Okay, so this is a linear congruence method. Okay, now another method up to your syllabus. Let me just mention it, though it is not so much effective like that of the linear congruence method. Even then, let us have a look at it. So the middle square method was developed by John von Neumann, and whatever this, I'm not going into the history. If you're interested, you can go through it. So let us see the algorithm for the middle square method. Start with a 4-digit number x0 called the seed. Okay, square it to obtain an 8-digit number. That means x0 square you have to calculate. Achha. Add a leading 0 if necessary. When necessary, how can we understand it? That depends on the next step. What the next step is saying? Take the middle 4 digits as the next random number. So what we are trying to use for to generate random number. What is the algorithm saying? You start with any 4-digit number. Okay, though we are saying it is set 4 digit, but actually you can use any number of digits. Okay, so and the number of digits you start with is the same as you have to take from the middle of the next random number. So suppose, let us give an example to explain it. So suppose we have started with x02041. So once you square it, you are going to get the number 41, excepting 0, 41658681. So what the second step says, ki you have to take third step says ki you have to take the middle 4 digits. Now if you want to take the middle 4 digits, but see, suppose 41658681, there are 7 digits. So how can you get the middle 4 digits? Middle 4 digits means what? On the two sides, the number of digits will be same. And here only this necessity lies. If I am, suppose here, as for this example, I am getting 7-digit number. Okay, from where I have to take the middle 3 digits. 4, 1, 6, 5, 6, 8, 1. If I want to take the middle 4 digits, which one will be the middle 4 digits? If you start taking from here, then on the right hand side there is 1 digit, on the left hand side there is 2 digits. So there is a mismatch, it cannot occur. Then you cannot say that 6568 is the middle 4 digits. Again, if I start taking from 1, then 1656 if I take, then also problem, because in that case on the right hand side there will be 2 digits remaining, on the left hand side there will be 1 digit. But this cannot be the case. What we need balance. That means if you take 4 digits, that should be from the middle. That means remaining digits, if I just omit this one, on the other two sides there should be equal number of digits. So I take this thing and justify, or rather balance this by putting a leading 0. That is what they said in the second step. He square it to obtain an 8-digit number. If it is not 8 digit, then add a leading 0 if necessary. It is not 8 digit, it is a 7-digit number, so you have to add a 0 in front so as to make it 8 digit, and then only you can take middle 4 digits. That means 4 digits from the middle. Okay, Achha. Then this number 1656 is your next random number. So x0 was 2041, this is x0, x1 is 1656. So in the next step, what I have to do? Again I have to square it. And so once you square it, then again from there either you will get a 7-digit number or 8-digit number. If 8-digit, then take the middle 4. If not 8-digit, make it 8-digit by putting a 0 and then take the middle 4. So that will, if you just check on your own, it will be 7423. And this continues. Achha. The main drawback of this method is that the middle square method is reasonable, but it is a major drawback. That means it is degenerative in nature. Degenerative in nature, what do we mean by that? Just look at the table. What we are getting? 2041, 4-digit number, 4-digit number, 4-digit, 4-digit. Here I have forcibly make it 4-digit, actually it is 3-digit number, right? Here I was 3-digit number, again 4-digit number I am getting, then 4-digit, but see the change after this step. 2-digit number you are getting, 2-digit, and this is going on gradually decreasing. 80, 64, 40, 16, 2, and then obviously if you continue, ultimately it will come to 0. Okay, so that is the main problem in it. Okay, so here after some steps, the number of digits, even if it comes to 0 or not, maybe it will come to 0 after infinite number of steps, but my computer cannot perform infinite number of steps obviously. So up to finite also, if this decrease in digits is fractable, that means it is degenerating with respect to digits in a steady manner. Steady manner means what? Suppose you see here I got 3-digit number, here I got 3-digit number, but at 6 step I am again getting 4-digit number. So there is this no steadiness in decrease of the number of digits, because you are getting 3-digit number, but after then in the next step and again in the next step I am getting again 4-digit number. So I cannot say that my number of digits is decreasing steadily, I cannot say. But after you cross the 7th stage, you can simply see if the number of digits has fallen to 2-digit only and just going on decreasing, it is not at all increasing. Number of digits has fallen and the number itself is decreasing. See 80, 64, 40, 16. So there is a decrease, steady decrease in it. So this is the degeneration which they are talking of. The middle square method as it is constructed will obviously in most of the cases face this drawback. It will degenerate. So suppose I want a random number generation for, suppose here how long I have continued up to 12 steps. Suppose you 13, 14 if you do, okay, what you will get after some step, it will go to 0. Okay, suppose up to 20 steps you continue and you go to 0. So if anyone asks me, giving this data ki x0 you have to take 2041 only, generate a random sequence of say 100 terms, can we generate? Answer is no, because here I can simply see if I continue up to 15 or 20 steps, it is going to go to 0. So where is the randomness? Okay, it is truncating up automatically after after a very small number of steps compared to what is required. So this is a degeneracy problem of the middle square method. So as a result of which it is less efficient compared to the linear congruence method. Okay. So that is what I have just mentioned here. With this sheet, random sequence does seem to be approaching towards 0. Okay. So this is the method here. Another thing is that you can try to do this one. Okay, this is just nothing but the huge lot of calculations to do. Use the middle square method to generate 10 random numbers using the initial seed as this one. Okay, once you do this, obviously you will be creating this chart. Okay, so you can understand if there is any cycling or not. That means after some steps whether your numbers are repeating or not. Okay, one thing I again repeat here, ki cycling, if I say, that means suppose I am saying ki one sequence is like this, ki 7 4 3 1 4 1 7 4 3 is coming, and then again 1 7 is coming, 5 8 is coming, and then again 3 4 is coming, then 11 21, suppose anything is coming. Do you say ki it is cyclic in nature? This repeating, there is a repetition? No, because 1743, okay, after you cover 1743, I am getting 1 here, then 7 here, but what about 4 3? I am not getting that. Again, if I say 3 4, okay, 3 4 is here, but what about 1 7 then? There is no 1 7 there. So if I am saying ki there is a cycle, then definitely the whole pattern should be repeating. That means 1743 you have got, again you should be getting 1743. That means once you have got this thing, then again you are getting this thing, then again you are getting this thing. This is the repetition of the cycle, not this. That means if only one term is repeated once or twice, you cannot say it is cyclic in nature. Only if the numbers and along with the pattern come back, all those numbers are coming back again, then only you are going to say okay, it is a cycling occurring. Okay, so this you can have to understand from here. Okay, and did each sequence degenerate rapidly? Okay, that means whether this number, the random numbers you are generating, is gradually decreasing in its length with respect to digits, and also obviously the numbers you are generating are obviously decreasing in the natural manner. Okay, so whether it is decreasing rapidly or after some steps it is decreasing for some steps, and the next step it is again increasing and again decreasing, and this goes on or not. But if you use this method, then definitely after some steps this method should give you the degenerate sequence. But how many number of steps, that is not clear. So 10 random numbers are asked for. So up to observing 10 random numbers, I have to answer this. I won't go after that. So it may happen that after 10 random numbers and 10 numbers you are generating, you are not getting any cycling, you are not getting any degeneracy. So up to 10 random numbers, I can say okay, the method is quite good. Okay, that means suppose I am using a system which can read up to 10 random numbers. You cannot read more than 10 random numbers. So up to that system, this method is good. So the question is posed like that. You have to generate this amount of random numbers, and you have to justify this algorithm with respect to that amount of random numbers which is asked for. I won't go up to 15 and say okay, see here after 15 if I go from 11th step it is degenerating. I won't see that. I have to stick to what is asked for. Okay, then what? Is there anything? There is any? Okay, so let us stop here.